So I'm Andrew. I'm one of the instigators of the RISC-V ISA project, but today I'm here representing a much larger group of people who have helped us bring up, the whole world of software on RISC-V. It's not just grad students, undergrads at Berkeley. A bunch of external people have helped us as well. We're getting to the point where enough stuff works so that more people are able to bring up their applications and libraries on RISC-V. And one estimate I've heard is that the cost of porting everything to a new ISA is somewhere on the order of $1 billion. So that's a little bit outside of our resources in our research group. So we definitely need help from the community in order to pull this off. And we welcome any contributions from you guys. GitHub pull requests, new libraries to be ported, and whatnot. It's not only a tremendous help; it's actually necessary for us to make progress. So before I dive in, I want to draw the distinction between two kinds of systems, tethered systems and standalone systems. So tethered systems are those that don't stand alone. They depend on a host system for boot and bring up. They don't have a complete set of I/O devices necessarily. They may or may not be able to run real operating systems, but that's not really particularly important for this distinction. The reason I bring this up is because at Berkeley, all of the silicon implementations that we've done so far have been tethered systems, because most of our research interest is in processor design and the memory hierarchy design, and for that it suffices to build test chips. Not only that, we don't have the resources to build entire real SoCs within our group. So in that regard, our chips are hampered by their lack of I/O. So we build tethered systems where we can proxy the I/O calls to a host system. But now that I've said that, I want to point out that we're interested in writing user and system software for both tethered systems and standalone systems. Most of the stuff in this talk applies to both. In particular, all of the user land, it speaks a common ABI, so the user land compilers and stuff apply equally to both kinds of systems. But the following bit is specific to tethered systems. So how do our Berkeley tethered systems work? The basic idea is that we offload the device I/O to a more capable host system. Concretely, it's probably like an x86 laptop or something like that. We do this at the granularity of system calls. So say a RISC-V user program tries to do a write to standard out or something like that to print a character to the screen. What happens is the context for that system call, basically a continuation, gets shipped to the host system, which performs the system call on its behalf, and then sends a return code back to the RISC-V host. Now, a couple agents have to conspire for this to happen. The first is a piece of software that we call the proxy kernel. It's a blob of software that runs on the RISC-V host machine. It has enough intelligence to support executing a single Unix-like process. It can handle some things locally, like say, mmap for memory allocation, but for anything that actually requires interacting with the outside world, it forwards the I/O-related calls to the x86 host system. So as I said, it speaks a subset of the Linux ABI, so it can execute normal Linux programs, at least those that don't do anything particularly, ambitious, like calling fork. So on the other end is what we call the front-end server, which is a blob of software that runs on the x86 host machine. Now, it kind of serves two purposes. One of them is to serve as the other endpoint for this I/O system call proxying. The other is to serve as the bootloader. So the first thing it does is load the ELF image of the proxy kernel into the target machine's memory, then starts executing, and then basically just acts there as a dumb device that does system calls on behalf of the user process running on the RISC-V machine whenever it's necessary. So those two can't communicate just like through the ether. There actually has to be a protocol for them to talk to each other, and that's the host target interface, or HTIF for short. Now, it's a pretty simple protocol. All it really does is provide the host machine the ability to read and write peek and poke control registers, read and write target memory, and whatnot. And there's a master-slave relationship here. The host is basically always polling the target machine to see if it has any work to do. The target's a dumb slave in this regard, which is great because it makes it very easy to build this, this stuff on the target machine, especially like in a limited silicon budget with limited design time. So we designed this setup to be like really lightweight and simple to modify. Like the proxy kernel and front-end server together are only about 5,000 lines of code, so it's really easy to extend them and muck around with them however you so desire. Changing gears a bit, I'm going to talk a bit about the available software implementations of the RISC-V ISA we have. And by that I mean things like simulators and emulators. So Spike is our in-house ISA simulator. It's written as kind of like it's an ISA interpreter, the same way you'd say like write a very basic JVM or something like that. It models a tethered RISC-V machine, so it executes the same kind of software that we would be able to run on our test chips. And in doing so, it faithfully models the host-target interface and talks to an instance of the front-end server, which seems ever so slightly masturbatory because these are two different processes running on the same computer, so they really don't need to go through this elaborate path in order to talk to each other. But that's how it works. That way, we can run the same software in both places. So we named our ISA simulator Spike for the golden spike that marked the completion of the first transcontinental railroad. And we did so because Spike is designed to be our golden model for how our RISC-V implementations are supposed to behave. Now, one serious downside of this name that I didn't realize at the time that we chose it is that it was Leland Stanford himself who drove that spike into the ground. But forgive that ignorance on our part. So Spike was, like the front-end server and proxy kernel, was primarily designed to be easy to modify and extend. So it is actually fairly fast. It runs about 200 MIPS on my Sandy Bridge machine, but it's written so it's very easy to do things like add instructions if you're trying to prototype some new thing or add an accelerator model or something like that. So you can go check out the code on GitHub. It's freely available. So our next software implementation that we know of anyway is a JavaScript-based simulator named Angel. One of our undergraduates, Sagar, put this together, and it's pretty damn cool if I do say so. It's a program that executes entirely on the client side inside of a browser window. It implements a RISC-V machine with integer ops, multiply and divide, and atomics, which is pretty much what you need to bring up the Linux kernel. And indeed, it runs the Linux kernel. So we designed this because we wanted to give people a lightweight RISC-V machine to play with, and they don't need to bring up a software stack or anything like that to use it. And so it's great for things like educational purposes and community outreach. Now, I understand from Sagar that implementing this thing was really quite a challenge, and that's in no small part because the only data type that's available to you in writing JavaScript code for numeric representations is the 64-bit floating point number, which isn't really so great when you're trying to model a 64-bit integer machine. And even so, the thing is surprisingly fast, given that hindrance. It runs at about 13 MIPS in Chrome on my Sandy Bridge laptop. And I understand it's getting faster by the week. We found out a few weeks ago when we were at ORConf in Munich that the OpenRISC JavaScript simulator runs at a ridiculously fast 80 MIPS on an iPad, and that kind of lit a fire under Sagar to make this thing go faster. So after the talks are done during a break session, you can go check this thing out. It's just risc5.org/angel. It's cool to play around with. So the final RISC-V software implementation that we're aware of is QEMU, which most of y'all are probably familiar with. It's a popular full system simulator. So that executes the whole RISC-V 64-bit, general purpose set of standard user level extensions. Now, unlike the other ports, this one was designed to actually model a standalone system. So it models full devices. Like there's a UART for the console device. We have an implementation of VirtIO and device drivers for that, so that we can model things like at an abstract level, model things like network and disks and talk to them from the target machine running in QEMU. It also actually speaks HTIF. We didn't really design it for this purpose because it wasn't designed to model a tethered machine, but that way you can run software that would be ordinarily targeted to a tethered machine, say to verify simulators against each other. So why would you use one of these implementations over the other? Well, Spike is good when you're trying to model hardware, when you want to verify the correctness of a hardware model. So Spike is something you can directly compare against instruction by instruction. In fact, some of the people who design RISC-V cores have a setup where they can single-step the Spike simulator and single-step their hardware and make sure that at every committed instruction that the state matches each other. QEMU isn't really designed for that kind of thing. It doesn't have the same level of visibility that Spike does, but it's almost an order of magnitude faster because it has a just-in-time compiler. And so it's actually fast enough to do things like real-time software development and debugging on it. It's probably only like a 3 or 4x slowdown versus running stuff natively. So people who are trying to port software to a RISC-V machine might find that this is the right way to go because experience shows it's a hell of a lot easier to compile and run stuff locally rather than cross-compile stuff. So QEMU is great for that purpose. You can also check out the source code on GitHub. It's freely available. So changing gears a little bit, I want to talk briefly about operating system support for RISC-V. The simulators are all well and good, but you need some software to run on them. So our RISC-V Linux port's becoming fairly mature. It supports the normal GNU userland, and we successfully booted Linux on some of our real RISC-V silicon. Where the kernel's developed against the 3.14 branch, which is the long-term one. I think current development's on like 3.18 or something, so it's not really that far behind. And development's ongoing. The thing's getting pretty mature and is getting close to the point where we can upstream it, I think. But there are a few missing features. Probably the most notable one is the lack of SMP boot. So you can only target a single core. That's something that I expect that we'll get up and running relatively quickly once the privileged ISA spec is a little bit less fluid, to put it a bit euphemistically. And the other thing that I think we're missing from the kernel that we want to add in the near term is the kernel instrumentation stuff. So you can trace activities in the kernel, understand why things are performing the way they're performing, even in production systems and so forth. So the Linux port, I think, is getting close to the point where we can upstream it, and once the privileged ISA is fixed, we want to do that. Again, you can go to GitHub, check out the source code. So the kernel itself is only so useful. You also need the rest of the facilities to have a normal OS environment. And recently we released what we call Pokey, which is a nickname for our port of the Yocto project, which is an open embedded based Linux distro. It's more like a distro generator. So it has the tools for you to cross-compile and build a fairly arbitrary set of packages that you can select. It'll automatically do things like download and build the tool chain, the Linux kernel, and so forth. You just basically type make and let it run for a while. It produces Debian packages, so it exposes a fairly normal experience for software installation as compared to a very stripped down configure, make install kind of thing you would do if you were doing this all from scratch. So it's pretty portable, and the install process is not totally dumb. It will abort when things aren't working right, so it's a good sanity check for our tool chains that everything's working okay. This is a little snapshot of the the build process or the configuration process. You basically just go down a list of checkboxes to say what you want. It's almost like a real computer or something. This is a place where input where help from the community would be very valuable. Even though our compilers and stuff are fairly mature, it takes a fair amount of effort to do things like port configure scripts and stuff like that. And I think a lot more packages could be ported with not that much effort. And so if you have something that you want to run inside of Pokey that you can already, please upstream send us a pull request and upstream whatever changes you made to make that happen. That would be of invaluable help. So like everything else, you can go check this out on GitHub. So finally, I want to talk a little bit about the compiler support for RISC-V. We've been spending a lot of time doing this. This is what I've been focusing most of my time on the last several months. The GCC port is finally getting to the point of maturity, I'd say. It's based on the most recent release, and we're actually thinking about moving to tracking the GCC trunk so that it'll be easier to upstream once the time comes. So it supports correctly, as far as I know, code generation for C, C++, Fortran, and OpenMP for all of the above. The OpenMP port is a little bit silly in that we don't have a multiprocessor OS to run these programs on top of, but if you want to run your single-threaded OpenMP program for some reason, you can do that. Of course, pthreads also works. That's the basis for OpenMP's port, at least in the GNU land. Our GCC port doesn't just target RV64G. That is the default target. It can also handle a variety of other ISA subsets for leaner systems. The BlueSpec guys, as was just mentioned, were kind enough to contribute some patches back to us to support code generation without support for atomics. You can still emulate atomic accesses by basically shutting the whole system down while the access occurs. They contributed as well the softfloat ABI, so you can run this on hardware that doesn't have floating point units without the dramatic slowdown of emulating those instructions. We're also closing in on passing all the tests in the test suite. It's now down to a human manageable number of tests that are failing, like low double digits, something that we can comprehend and manually fix one by one. And once that's done, the GCC port is nearly ready, I think, to be upstreamed back into the GNU Hive mind. at least as long as they're not feeling too ornery. I think the generated code quality is okay, but not perfect. I think if there were one thing that people outside of Berkeley could contribute to, it's whenever you notice our compiler is doing something stupid, send a patch that fixes it. At least if you're familiar enough with the GCC internals to do that, because we can only look at so much code and see so much bad code generation to fix ourselves. So like everything else, you can check out GCC on GitHub. That repo actually contains more stuff. It's also the binutils, the C libraries, and whatnot. Speaking of, the binutils port as well is also pretty much done. It has full support for dynamic linking, and as of a few days ago, actually as of yesterday, we can now produce core dumps in Linux and GDB them to see why your program crashed. That's based on work that also the BlueSpec guys originally contributed. They contributed a GDB port with support for remote debugging for their cores. So I think binutils is probably going to be the first domino to fall as far as upstreaming this stuff goes. I think that may well happen within the following semester if we're lucky. So I want to focus on one particular part of the binutils because most of our ports are pretty vanilla. This is the plus of having a simple and straightforward instruction set. But the binutils port does have one feature that's a little bit exotic. So in RISC-V, full 32-bit addresses, like say for function calls or global variable accesses, take multiple instructions to generate the sequence necessary to perform that access. And we'd like to take advantage of the observation that spatial locality really does exist, and often things are not that far away from you, so you don't need to generate these multi-instruction sequences to do things like say call functions. Now, unfortunately, the compiler doesn't have enough information to determine this at compile time because, say, you might be calling a function in a different translation unit, and so it needs to generate a relatively general code sequence that could call anything. So we just accept that's the case. The compiler always generates kind of crappy code for things like global variable accesses and function calls, and then we punt to the linker to fix it up. So the linker will then do things like substitute a multi-instruction sequence for a call with a single instruction. And it sounds straightforward, but the machinery to get this working was actually kind of a bitch. And because in particular the linker must go through all the code and fix up offsets for branches and things like that. Since the relative program counter values have changed since code was deleted. Now, the most common use case for this is function calls. So you see there the RISC-V idiom for calling a general 32-bit PC relative address. In the common case, so our JAL instruction, our jump and link instruction, on the other hand, can only handle a megabyte of displacement, which is actually good enough for nearly every function call in nearly every program, except for very large ones, like say the CAD tools or something. And so we'd like to leverage that, the fact that most functions can be called with one instruction. The linker, once it knows the relative addresses, can delete one of those two instructions and swap the other one out for a direct jump. Likewise, global variable accesses can be relaxed the same way, and although I didn't show it, there are also myriad relaxations for things like thread local storage. Now, all in all, this is only one data point, so take it with a grain of salt. But this all resulted in about a 7% reduction in code size in the Linux kernel, which is not a factor you get that often. So it's a good thing to get. So also in the toolchain land, we have a couple of C libraries. The main one to use for say like workstation class stuff is if you're running Linux is the GNU C library. It's the default one used if you use the RISC-V Linux toolchain. It's a pretty full-featured C library. It supports things like LD.so, the dynamic linker, pthreads, and whatnot. And that's getting to the point where I think we're going to upstream that this year as well. Now, we also provide support for an older version of NewLib, just because we haven't been updating that. It's more suited for embedded situations because another way of reading the term full-featured is bloated, and for embedded systems, you don't need all those features like say name resolution or heavyweight kernel thread support, and so NewLib is a more suitable library for those situations where code size is paramount. It also has fewer dependencies on the OS. So for example, the simple proxy kernel that I mentioned at the beginning of this talk can handle anything that NewLib wants to do. So a recent development is that the ABIs for these two libraries have been unified. So generally, you can run NewLib programs on Linux. You can run Linux programs on the proxy kernel as long as they don't do very much interesting stuff. Any place where they're diverging, we intend to fix it. Basically, the insight is, why do two things when you could just do one thing? So GCC is not our only compiler. We also have an LLV import. So we only use LLVM for doing code generation for user level software. As far as I know, it can't like build the Linux kernel. The reason that we started an LLV import is not just because we like porting software, but because LLVM is a hell of a lot easier to work inside of than GCC, and for our research purposes, we want to do things like write compiler passes for, say, auto-vectorization, and that is nightmarish to do in the legacy Stallman code base, and so that's why we started working on LLVM. It's progressed quite a bit. Our original port was just based on the 3.3 release, but now we're actually tracking the LLVM active development on their trunk because, as with the other packages, we do have ambitions of upstreaming this eventually. So we would love, for help on the LLVM compiler, both correctness things and improving code generation. I think some of the things that are missing right now is, the test coverage isn't so great. There are some code quality issues. We want to clean that up a bit. Like GCC, improve code generation. It's not perfect yet. And one major thing that's missing is the assembler and disassembler, what LLVM refers to as MC for machine code. Right now, whenever we generate code with LLVM, we pass it to the GNU assembler and linker. But LLVM, of course, is going to want us to port to theirs as well. So you can go check out the code on GitHub. So one of the things that's come along with our support for LLVM is the ability to compile OpenCL code. So between Clang, which we use as the front end for compiling OpenCL, and Pockle, which we use as the library implementation, we can now generate OpenCL code that targets RISC-V scalar cores. So that means you can target, say, like a RISC-V multiprocessor with a single OpenCL kernel. That's kind of neat. That wasn't really the reason we were doing this. As I said before, some of our ambitions include being able to target vector machines from LLVM, and the missing work there is on code generation for our UC Berkeley vector machines from OpenCL source. So that's about it for LLVM. So one final thing to talk about. How do we make sure any of this shit ever works? So we have a simple verification suite. There's a handwritten test for every instruction in the ISA that whenever we make changes to the hardware, you have to pass all of these. They don't really get very good microarchitectural test coverages. They just make sure, for example, that when you add 1 and 1, you don't get 3 as the answer. So these tests can run in a variety of different, what we call test virtual machines, to test different facilities, like say the virtual memory system and whatnot. So the tests and the environment they operate in are orthogonalized. Along the same lines, we have a handful of handwritten micro benchmarks that like things like quicksort and matrix multiplication and stuff like that, which both serve to make sure the hardware isn't screwed up and also serve as relatively rudimentary performance diagnostics. The final point on our verification suite is the random test program generation. We have 2 programs aptly named Torture and Schadenfreude, mostly because of the pain that they cause us. And they do things like test combinations of instructions and microarchitectural events that are not really likely to occur in C code. If you stare at things that GCC and LLVM emit, they emit like fairly templated looking code. There's not a whole lot of creativity in instruction generation. And so like a lot of bugs, especially say in your microarchitecture's control, could slip through the cracks if you're only using compiled code to test your stuff on. So that's the gap that we try to fill with Torture and Schadenfreude. They're not quite ready for prime time. We haven't released them yet. We need to clean up the code and improve our test coverage. Like for example, we don't support generating loops yet. We only support like a single-use control flow. But we intend to release that once it's done, and then other people can help improve test coverage. So all in all, our verification setup is probably the weakest part, the weakest link in this chain, and we'd love help from external people to improve it. If you find a bug that that our test suite failed to catch, please write a test case that breaks your thing and submit it. That'll save other people lots of pain down the line. So you can go check all that out on GitHub as well. So that's actually about all I have. So if anyone has any questions, I'd be happy to take them now. I'm not aware of anyone working on U-Boot. So we do have some people who are working on bringing up Core Boot, but not U-Boot yet, no.
And yeah, we've had some interest from UEFI as well. Maybe they'll give resources to do UEFI for this.
Do you have any way of benchmarking the quality of your GCC compiler against GCC compilers for, say, ARM or x86?
So it's a little bit difficult because there's two moving pieces here. For one, there's the quality of our compiler report, which is certainly not as optimized as theirs. And for two, there's the difference between the ISAs. So I can tell you that looking at static code size for our GCC port versus, say ARMv8, ARMv8 binaries are ever so slightly smaller, and I don't yet have enough information to pin that on our compiler report or on differences between the ISAs. There certainly are some features in ARMv8 that will reduce code size relative to RISC-V programs. On the other hand, RVC will reduce code size substantially relative to them. So yeah, I guess I don't know is the short answer to your question.